Welcome. Thanks so much for joining.
Great. Thank you so much, Sambuddha and Chris. I'm very excited to talk to all of you today. My journey has been a winding path. So I grew up in Malaysia, which you can see is all the way over here. So that what is in red is Southeast Asia. And then I went to high school in Singapore. And then for college, we had to go abroad because there are actually racial quotas in Malaysia for university admission against my racial group and really against anyone who's not in the majority race. And I was lucky enough to go to Yale for my undergrad. So the first time that I stepped foot ever in the US was when I arrived as a freshman for orientation in Connecticut. And it was a huge culture shock for me. I'd spent all my life in Asia with, Southeast Asia with different norms, system of governments, ways of interacting. And then here I was in Connecticut surrounded by mostly Americans. And besides the culture shock, I was also feeling injustice about the way that my people in Malaysia are discriminated against. And so even though physics was my favorite subject in high school, and I trained hard for the physics Olympiad and I won a gold medal in the Singapore Physics Olympiad, I actually abandoned physics in my first 2 years at Yale and I turned to the social sciences. I wanted to make the world a better place, seeing all this injustice, and I felt physics was useless. I wanted social change, and the social sciences seems to me more promising there. Then what happened was that in my junior year as a sociology major, I took introductory physics again with Shankar at Yale. And you may know him because he's written several famous textbooks, and he's also been recognized as an amazing teacher. So this is an article that's celebrating a teaching award that he won quite soon after I graduated, that highlights some of what I loved. For example, that he, introduced quantum mechanics in an introductory class, mind you, which is pretty gutsy. I mean, usually introductory physics does not contain quantum. And also that he's just really funny. And his class made me fall in love with physics again. I still remember the moments. I knew about classical mechanics from high school, but quantum mechanics blew my mind. It was so counterintuitive and so surprising that like an electron could interfere with itself. That's not something you see in everyday life. And so then the summer after that, I was doing research for sociology since I was a sociology major, and I had to do research for my senior thesis. And as I was doing it, I realized that I wasn't studying sociology for the right reasons. In that, like, for me, sociology was a means to an end. It was because I wanted to make society more fair. But I didn't love it. I wasn't fascinated by it the way that I was by physics. And I realized that I had to follow what was given to me, in terms of like what I loved and, what I was good at, like what was my path, And I mean, it's been very interesting because, even after I switched back to physics, this question is still there, right? Like, is physics useless, or can I, doing physics, make the world, still have impact on the world, make the world a better place? And I mean, it's a very interesting question for me because that desire is there, even though, I realized that I really had to say yes to what was in my heart and to, what I could do. And thinking about it, I think that, the answer is that yes, it is possible to make the world a better place through physics. And I'm going to come back to this later. So this slide contains a spoiler. As you see, I went to MIT for graduate school. And after 1 year in Cambridge as a Gates Scholar, and I went towards quantum mechanics because that was what fascinated me. So now let's talk about what I did during grad school. And within quantum specifically, topology really fascinated me because that's very cool. And so let me give you an example here, since not everyone may be on top of topology. So this is the quantum Hall effect, and this is a schematic. So essentially in this canonical example, this is a two-dimensional electron gas. And here, in the presence of this external magnetic field, electrons will make closed cyclotron orbits in this semi-classical cartoon. So in the bulk of the system, they will just move around and they won't go anywhere. The kinetic energy is they're pinned, and so the kinetic energy is quenched. On the edges of the system, you can see here that the orbits can skip off and form these chiral edge currents moving, in one direction on one edge and in the other direction on the other edge. And these edge states, these edge dynamics that now dominate the system because, these guys are just not going anywhere. These edge states have the property of being robust in that, right now they follow the edges of the system, but you can imagine that if you deform this thing or you introduce some tear in the system or something, that you're not going to destroy the edge state, right? You're not just going to get rid of it, but instead there will be a new edge that will be formed and the edge state will go around it. So this robustness is very nice. And overall, this edge state is an example of a global property of the system that is much more than just this individual local behavior of the individual electrons that by themselves would just go around. So that's the quantum Hall effect, and specifically the really this is an example of the integer quantum Hall effect. You get, you can measure sort of channels of electronic charge going around the edges in particular. And as you crank up the magnetic field, what you see is that the quantization of these electronic channels starts to go down. So you get fewer and fewer electrons in each of these edge states. So the integers go down from really high, then 4, 3, 2. And what was really surprising was that when they kept turning up the magnetic field, they started to see fractions, which is very strange because, electrons are indivisible particles. So, what is a fraction of an electron? So this was very surprising, and they won a Nobel Prize. Well, actually, before this Nobel Prize, there was another Nobel Prize awarded for the integer quantum Hall effect, and then this Nobel Prize was awarded for the fractional quantum Hall effect. And these particles, they are very surprising. They're robust and they have interesting properties, and so they have been proposed for fault-tolerant quantum computation because of their unique properties. But they are also the state is also measurable at very cold temperatures, millikelvin temperatures, and in very clean systems. And so for millikelvin temperatures, you need things like a dilution refrigerator, which you always need to be feeding it helium and maintaining this vacuum, very precise conditions. It's very challenging, to say the least. And so my first paper as a graduate student was actually to propose a new platform for the fractional quantum Hall effect that could potentially support this state at much higher temperatures, maybe even room temperatures. So here we went away from traditional semiconductors to a completely different platform, a lattice system, which was later on, this material was later on synthesized, and many of our predictions were later on confirmed by the group of Joe Chikowski. This is this Brillouin zone of the Kagome, which is a hexagon, and then looking at the excitations in here. And this was a direction that I found very interesting, to think about how these very beautiful physics phenomena that at the same time that's often locked up in very niche systems can be potentially realized in systems that are more accessible in new platforms. And this can come about through thinking about theoretical design in a creative way. So thinking about how emergent phenomena can be analyzed and seen in a broader variety of systems started to get me thinking about other systems that show really complex emergent function like the brain. And so here for my postdoc, I moved into thinking about the brain and developing global metrics that could relate to the function, cognition and development. So for instance, one of my papers here was I used data science and linear classifiers to probe the dimension of brain representation. So essentially measuring brain activity and looking at how much effective space that the brain data occupies. And what we actually found is that those who learn faster have a higher dimensional representation and a more efficient representation of their brain structure while they were learning a particular task. And so, these ideas about predicting emergent structure that can support also like robust system function from ubiquitous systems that we see around us, systems that are more and more accessible, everyday systems, biological systems, really underpins what I'm thinking about in my group today. And especially starting to think about living systems, because that is a real challenge. Because one question is really, why is it that living systems can exhibit such stable and robust function? Your brain networks the structure looks different from mine, or they will respond differently to even a given stimuli. They'll light up or signal in a different way, and yet we can communicate and maintain similar biological functions. Or if we go down to the small scale of cells, there's often a lot of stochasticity there. Or if we think about like genetic copy numbers, those are often very small. So there's a lot of heterogeneity, a lot of stochasticity, and yet living systems can show robust function, for example, persistent timescales in circadian rhythms or memory. And how to describe this emergence is the challenge for physics, because statistical mechanics typically assumes identical particles in equilibrium and isolated from the environment. So thinking about emergent dynamics is really interesting, whether it's the learning of novel stimuli, for example, here, or if we think about a global oscillator or the synchronization of multiple oscillators. And where by emergence, what I really mean is that the system here comes together to show dynamics that's much more than a sum of each part. So what you see is much more, like in the quantum Hall effect, or like in these examples. And as a theoretical physicist, what I want to ask is, can we predict such global dynamical or functional states analytically? And analytically, because computationally, honestly, this is kind of a beast. I mean, computationally, if you try to do it, the parameter space is huge. Let's say you just have like 6 variables in your system and you want to just check 5 values each, just over like 15,000 conditions. And here we're checking dynamics. So you can't just like, you have to like observe how the system goes on for some time. So you do that, and you do that over multiple conditions. Even if you manage to understand like one set of variables, it's very difficult to transfer the results to a new scenario, or to see what happens if you like add a variable, like, I mean, to understand just like how robust the results are, if you look longer, would it change? Like, how do you quantify that? And then given the noise in biological and other experiments, we don't have the detailed data over so many variables to compare the results to. So here it would be really great to develop a framework for different kinds of, for example, specifically here for these different examples of emergent behavior. But now I've also included the stochastic growth and shrinkage of a microtubule, which are cytoskeletal filaments that are important for the growth and movement of a lot of cells. And while these different phenomena appear unrelated, for sure, in our work we managed to show that such dynamics can all hinge on the edge state of a topological phase. And this sounds formal, but this does depend on a lot of condensed matter physics that is well developed. So now let me show you some of my recent work here. And this is essentially, using how topology now has started to really take off in a lot of classical and stochastic systems. In these papers from a couple of years ago, they showed developed proposals for stochastic systems, and these are one-dimensional systems. So here again, you see that there is some kind of bulk and some winding in the bulk and an interface, where at this interface, they found that you could have a buildup of probability density here at this interface or this edge. Now, of course, in a one-dimensional system, this edge is necessarily zero-dimensional, and so it's not going anywhere. I mean, it's stationary, it's polarization at best. Together with Jaime, who was in the office next door, we asked the question: well, can we obtain propagating edge transport in stochastic systems like in a quantum Hall? And remember, that's also because there's very desirable properties that edge states have if we use such a description. They are robust so that if we have an obstruction or something that blocks it, the edge dynamics will still remain. So you might be thinking, well, this is a little strange. How are we going to go from this 2-dimensional electron gas to living systems? Living systems are 3-dimensional, and yes, they are. And however, the link that we made was to think about a space in the space of chemical configuration space, so the space of chemical reaction space. And in fact, there are many out of equilibrium cycles in reaction space that are fueled by the consumption of ATP. So for example, this is an example of chemical reaction space, like phosphorylation, dephosphorylation, adding of a component, removing of the components. And not only that, we actually, it has been noticed and we identified futile cycles as being able to play the part of electron orbits, because these cycles have been observed where they have these like very energetically expensive reactions where they do these cycles, but it goes back to itself. So it's like, well, what's the point? It seems to leave the system unchanged, and yet such cycles appear in many different systems. And so here, these we realize that these futile cycles could play the role of electron orbits, like in the bulk of the quantum Hall effect, where they seem to go around without doing anything. And what these local orbits in the bulk could do is that they could then support chiral edge states on the edges of configuration space, which now could then give rise to these global emergent cycles, for example, a large oscillator or something like that. But now that's governed by the physical constraints of the chemical configuration space, instead of having to get, let's say, a global cycle by fine-tuning all of the steps so that they add up exactly to what you want. So I'll just show a few more slides just to show you how our model looks like, and then I'm going to pause for questions. And so here, just a very simple model. This could be in chemical configuration space. This could be adding and removing monomers. in this polymer system. So this polymer has two types of monomers, this purple and this green monomer respectively. And these numbers are the numbers of these monomers. So 2 purple and 1 green. So here I add a green, I add a purple, I remove a green, I remove a purple. And not only that, we also allow for an additional process that primes the system for the upcoming transition. So in here, I prime the system to add a purple. So then I can describe this internal state of the system, what is going to happen next by these tags A, B, C, and D. So A says, so add a green, here add a purple, and there's 4 internal states. So then each state now has 3 indices, these numbers which we can call X and Y, and this other tag. But now this allows us to see that now for the same monomer configuration, we can have 4 different states so that we know what's going to happen next. So for these, the same configuration, these A, B, C, D. And here we also allow for transitions between these configurations shown by these dashed arrows. And what this allows us then is laying it out in this way, we can then see that these 4 internal states can form the unit cell that we can then tile. So this forms the basis that we can then tile in a larger configuration. So here, this basis is in this blue square. So then if we move it along in configuration space, where now this x-axis is a number of purple monomers, this y is a number of green monomers, we can tile a different geometry. And so here you see that this closed loop with these solid arrows corresponds to this loop that I showed you here. And this loop with these dashed arrows corresponds to this loop that I showed you here. And going to lattice space allows us to see nice things, most of all, to use topology, where we can use topology then to show that when these black rates are now faster than these gray rates, the system, once it hits the edge, it will stay there. And you can see this just by following these arrows. So let's say you're here, you can only move forward. And here, you will likely move forward because, well, black is faster than gray, so you'll most likely move forward here. You'll move forward again, he'll let you move forward, and so on, and you'll just go around and you'll end up staying on the edge here. And then this is where you can see the system is protected in the sense that, now here, even if we have obstructions or something missing, the edge state will not be destroyed, but will just go around. And we can show nice things, for example, that this edge state is exponentially localized, so that even when the system is fairly small, that this edge physics is robust. And some comments here. What is nice is that it's very cool to see that this beautiful physics that's mostly associated with quantum systems, and not only quantum systems, but often very regular and clean quantum systems. But that by going to configuration space here, this regularity and this lattice structure can come about from thinking about assembly and disassembly of components. So that now we can use these tools in much more ubiquitous systems in the space of molecular configurations. And there are tons of biochemical processes that have directed cycles. So, this formalism could have a big impact on our understanding of how they arise, how these cycles arise, as well as to identify the conditions that support them. So now here we just see that so long as black is larger than gray, this will happen. And this is prediction that we can test. And in fact, because this model contains only 2 parameters, this particular one at least, the black and the gray, so then, this is a prediction that becomes easy to test because we only just have a couple of things to propose. And so this could be useful when we think about molecular mechanisms and how this can underpin, let's say, biological function, which could be useful for applications or translational applications. So as a physicist, I'm still trying to impact the world by thinking about how this very rich and beautiful physics that we see, that we're used to, can be made more accessible and totally new and ubiquitous platforms through theoretical design to make it relevant to the world that we see and touch around us. So I want to stop. I know that a big goal of this Chilloquium is to really chat, and so I before I go further, I just want to see if there's any questions, any thoughts. I'm happy to discuss any part of it on what I showed.
Yash, go ahead.
I think my question was to the integer Hall thing, integer quantum Hall effect. So what would happen? So we showed that on one side we cut it, so it's there's a half a spin on one side. But what would happen on the corner if it was not it was not fully able to do a full half turn? the electron.
Yeah, so that's so let me just go back to that slide. Sorry. How do I? Okay, so in here, yeah. Well, so firstly, one thing that, well, firstly, I mean, I guess you could imagine that, you know, it could just bounce off and then you know, it wants to keep bouncing, so it'll keep going around. But one thing that I also caution you is that this is a semi-classical cartoon of a quantum mechanical effect. So while this cartoon is actually extraordinarily useful, I mean, honestly, it's much more useful than just like, you know, a little cartoon. But at the same time, you know, it is a quantum mechanical process. So somehow, you know, I mean, essentially the electron, you know, you can think of it as definitely a probability distribution. It will scatter off in some way. And this orbit is really its path. So you can think, I mean, you can definitely think of a quarter path. So I think that's fine if that's what, you know, the center of mass of the orbit is. So I think it is possible to have a quarter and it will just keep going. So in that sense, the electron still remains as an electron, albeit in a wave function form.
Right. Thank you.
Yeah, sure.
Mitchell, go ahead.
Oh, yeah, thank you. I think the models that you have discussed so far are a very kind of like abstract model from the physics or some condensed matter background. So I was wondering like whether like using this kind of model like directly to the biological system, like brain or molecular kind of biological system, should we incorporate some kind of biological like knowledges or some like biological peculiarities in this like system as well?
Yeah, that's a great question. Yeah, I definitely, okay, so we were here and definitely, you know, this forms the basis for many things. I mean, this really forms the description that you can describe many directed cycles. And of course, we wanted to think also about how this could be relevant for biological systems. So yeah, I mean, I'm very happy to show a couple of examples if that would help. I just didn't want to, you know, overwhelm you guys with too many details right away, because this is really the, you know, the conceptual part of it. But yeah, why don't I go ahead and just show a couple of examples. I think you had two very good parts of your question in there. One of which was, you know, how can this be relevant for biology? But not only that, how can considerations that are specific to biology maybe change some of the description? So let me try and you know, show you a few examples. So one example here, you know, is thinking about sorry, so let me just yeah, so could be to think about you know, so as you can imagine, going around configuration space does seem like this, like, you know, biological oscillator or a global cycle shown by you know, an oscillator. And there are many different oscillators in biological systems, and here, you know, I can discuss an example of how this will work in the Chi-ABC system, which regulates the circadian rhythm of cyanobacteria. Is just much simpler than what you find in you know, eukaryotic cells. But in this system, so you can see, which has been, you know, isolated, the monomers of this system can have 4-state directed cycles of phosphorylation, and it can also assemble into hexamers. And not only that, these monomers can have active and inactive conformation. So already here you see this large phase space of different possible transitions. And, you know, how can we understand the dynamics in this system that gives rise to its timekeeping ability? So here in our model, we focus on just 2 transitions per monomer. So here we have conformational change and phosphorylation, where we show the first one going from this diamond to this circle, and this phosphorylation here we show by adding this yellow circle. And so now here we propose this 4-state cycle in which, you know, you can undergo conformational change, and then conformational change, and then dephosphorylation, and then conformational change again, and then phosphorylation. And then just as we did before, we again allow for another internal process that can prime the system for the upcoming transition that we'll label A, B, C, D. And then now we can have internal states for the same configuration and transitions between them. And it is exactly what we had before, you know, this like 4-state basis. So then we can lay this out, you know, in this larger geometry. And now, because we have a hexamer, so essentially we have 6 possible changes, I mean, for all the 6 monomers. So this essentially forms a 7 by 7 lattice because the indices can go from 0, 0 all the way to 6 by 6. So this is the same as what we had before, just larger. And then in the topological phase, then we would get edge states that move around the edge, right? So essentially we would get all of the monomers would undergo conformational change, all of them would undergo phosphorylation, all of them would undergo conformational change again, and all of them would undergo dephosphorylation. And interestingly, this is actually exactly the same dynamics as what has been proposed in this system in which they proposed the same thing. All the monomers undergo phosphorylation, all of them undergo conformational change, dephosphorylation, and then conformational change back again. But just that for them, here they have to ignore like all of these possible intermediate transitions, or like assume that these are much smaller than these, that somehow breaking the invariance between C0 and C1. Whereas in our system, we actually still allow for all of these intermediate transitions. We just didn't draw them, but they're here. It's just that in a topological phase, the transitions are still there, but the system will just naturally show these dynamics. And so this could be something that could be really nice to test, by looking at these systems. This work is pretty new, but I'm looking forward to talking to biologists and seeing if we can test these systems. I also have a couple of other, maybe two little examples. So maybe I'll just show that first, just so that, and then so that everything's there. So let me go to that. So yeah. So in this one, yeah. So for this example, it's easier to go to. We also have an alternative model. So far I've been showing you 4 states with 4 internal states, so a basis of 4. So you can also have a basis of 3, where now the first number can describe the number of monomers. The second number can describe some kind of, let's say, conversion of that monomer. So here shown by adding this purple little purple square. So these transitions could be, converting the monomer, adding an unconverted monomer, and then removing the converted monomer. And then again, we have this, internal process that primes the system, and then transitions between the different internal states of the same configuration. And then interestingly, this 3-state model can be laid out now as a cogomate lattice. So if we repeat this unit cell, this becomes a cogomate lattice. And in the topological phase, you can again check that, when the black is larger than the gray, then again here, you'll move forward, you'll likely move forward, you'll move forward, and so on and so forth, and you'll keep going around this edge. So now if we just have this, this gray and this black, which is probably also, in solid state, this is probably typically what we have, just 2 different electron hoppings or transition rates. But in biology, as you were asking, biology can do all kinds of like different things, right? So we could change one of these rates. And actually here, what we have is that we can actually have 3 black rates and 3 gray rates. So let's say we change one of them. Let's say we change this upper right one, which, in biology, one of these rates could be different. So let's say we make this one a little bit faster, so that now this one is faster than the other 2 gray rates, but it's slower than the black rates. So what we would have here is that now this edge would be faster than these 2 edges. So then if we plot, let's say the number of monomers here, which is this edge and this edge, because this one is just a conversion. So if we plot this will go here, it will grow, and then it will be fast, and then it will shrink slowly, it will grow. And so this is what we do expect, it goes up here, and because this is much faster, it comes back down very quickly, it goes up and it comes down. But what you also see is that sometimes it doesn't make it all the way to the top, because here you can see that because this is faster, sometimes it cuts out, goes by these circles, it doesn't make it all the way to this edge. And what is nice is that this is actually very reminiscent of the dynamic instability of microtubules, which are these cytoskeletal filaments that have this like random, like shrinking and growing, and like no one understands, like, why is it that it's so random? Why doesn't it grow to the same part each time before it shrinks? And we can capture this like very complicated biochemical process just by having 3 rates in the system. So this is something that's nice, and definitely, it could be something that we can, now bring to experimentalists and think about what we can test or check there. So this is one example of how thinking about biology, which is now to say that, okay, in solid state, it's not really so easy to just like change like one of the hoppings. But in biology, it's quite possible that chemically one of the rates are different. And lastly, I'll just show one last little example, which is that when we think of these things as, again, like from a biological point of view, as let's say these are actual chemical components that we're actually like assembling to become part of the system, that could be a regime in which, or a situation in which we have two systems, let's say, that are taking monomers from the same pool. And so when they finish consuming them, then, then there's no more of that monomer. So then they're coupled together in that way. So here we actually have these two systems. One is, it starts to consume monomer starting from 0 and it moves here to the right. And this one, it starts from the right here and it starts moving towards the center. And it'll consume, monomers from the same pool until they meet each other. When they meet each other, they'll have finished consuming monomers in the same pool. And then they'll have to go to the next reaction, which is to go up. So then they'll start doing what you saw, which is to go up. And already you see interesting things, right? When they go up, they have this shared boundary, and that shared boundary keeps changing because it's a stochastic system, which again, you never have in solid state systems. But also after a while, you see that they start to show this, the competition makes them show this, one goes up at a time. So they have this anti-phase synchronization, which you can also show here, which is kind of neat because you actually get this anti-phase synchronization without direct interaction between the systems, which is what our normal mathematical models have to impose. But just by imposing shared physical constraints that this emerges here. So that was a long answer to your question, but yes, we are trying to think about the biological applications and compare them and think also the reverse. How can thinking about biology then inspire us to think about new things like dynamical boundaries, which we don't have in solid state systems. So there's a lot of rich things here to explore.
Yeah, go ahead, Mitchell.
Oh yeah, thank you so much for the detailed answer. And I think these examples are really comprehensive for me to understand the things. So I was wondering, so when you design this kind of biological model, you don't want to incorporate too much details, and also you don't want to miss out too much biological things as well. So you have to find out some balance, how much biological peculiarities you want to include in the system. So I just wondered how the process you decide which kind of the biological kind of characteristics to be encoded in the system, and then how it is decided in the research process as you are making these kind of models in the research.
Yeah, that's a great question. I think that kind of thing comes out very naturally from the training as a physicist, right? As a physicist, normally we try and simplify things, and this is even more, I think that it depends on your goal. Here we really were trying to have a theoretical description, or something that we can map back to theory, which you can also show a little bit more of the kind of math there. And if we do that, really, it really helps if we have just a few parameters, right? Which is also one advantage of our models. You see there's very few parameters, because the thing is that once you start to say okay, I will just, simulate something, it's easy sometimes to start to simulate a lot of different things, and then it can go up very easily. So I would say that in here, in here, the training helps, and also just what these models are help. So for example, the fact that we have a two-dimensional system, or this is two-dimensional dynamics, means that already we tend to start thinking about, okay, what are sort of two main processes in the system. Yes, there can be more, there can be others, but maybe those somehow, maybe things like, let's say, internal states, or things that you can add onto the basis. It's like a more decorated lattice, if you will. But this lattice in and of itself has two main rates. And already, if you say two main rates to a biologist, they're like, what? They're like, no, there's way more stuff that's happening. But actually, if you think about it, even if there's a lot of stuff that's happening, which I'm sure there is, if you start thinking about length scales and breaking down fast and slow, there's probably a regime in which you don't have to think of all the the length scales that is actually pertinent in that moment are probably just a few, because some are not relevant on the length scale, on a time scale that you're looking at, and so if you start thinking about how time scales and length scales can help you sort of divide things, there's probably only a few things to look at. So I think this physics lens is also very refreshing to say that, all right, let's really be very thoughtful about which axes you want to focus on in the system. But it's a constant dialogue, right? And I think that's the fun part. You go to biologists and they'll be like, no, you didn't include this, and you're like, well, how about that? And so that's the fun part. You try and sort it out together. So
Cool. I have another question that was submitted by someone in the audience. This is referencing the earlier part of the talk, and the question is, you mentioned that you wanted to improve the world in some real way?
Yeah.
As you were switching to theoretical condensed matter physics?
Mhm.
Is this something you were thinking about? Yeah.
So is the question about like how does Kanban improve the world through theoretical condensed matter physics, or is that the question?
Yeah, I think that's a good way to approach it.
Yeah, and I mean, I think this is like it's definitely a big question, you know. And not only that, you know, firstly, the answer is yes, because, you know, it's not like I was caring about the world in one moment and then I switched to physics and I was like, okay, now I don't care about the world can do its own thing. I mean, of course not, right? I'm still the same person. And I think that so it kept on being a big question for me, but I think like that has, you know, really also changed the way that I wanted to do physics, right? Firstly, what I would say is that the answer is not obvious. You know, it's not like, you know, like my dad's an engineer, you know, so my dad built something and we can see like, oh, he built that, you know, I mean, like, you know, there's nothing I can like point to that I built with my own hands, right? So firstly, it's a question that's open, but that's the amazing thing. Because the question is open, I can never pretend that it's solved, you know, so it's something I have to ask myself all the time, you know, like every day, to be like, all right, how am I contributing to the world today? You know, and it can be in different things, right? It can be on a level of research, you know, which is why I'm so passionate about thinking about how I can make also beautiful physics relevant and useful to the world, right? And thinking about systems that can be, you know, accessible, that can be seen and dealt with and interacted with in an everyday way, because I think that physics has a lot to contribute to the world. But it also comes about in other ways, right? You know, how I, you know, why I'm interested in you know, talking to students, you know, why I'm interested in working with students, why I'm interested in educating, why I'm, you know, and also the way that I think about research and how I interact with the people around me, right? So, you know, I don't, you know, I don't want to be, you know, you know, crotchety, angry physicist trying to do things on my own. I mean, you know, because I do believe that somehow, you know, that it's important for us to grow and to learn together and to help each other. So I think there's many ways in which the answer of like how I can make the world a better place still comes about as a physicist. And in regards to my own country, you know, I still think about that a lot, right? I mean, you know, I'm not back in Malaysia right now, but, you know, I think about ways in which, you know, how can I maybe go back and teach, or, you know, how can I, you know, think about connecting with students there. And so it's also questions like these that are still very alive for me, and I think change the way that I do physics, right? And the amazing thing is that, like, when you keep the question alive, what I found also is that the answers come in ways that I wasn't expecting. You know, I found myself like maybe an opportunity to interact with someone that I didn't expect, or, you know, an opportunity to work on something that I didn't expect, that really opened up doors for me that I really found could be interesting, or could be and help me to really engage with the outside world. So I will say that, you know, keeping the question alive is, if this is a question for you, which I think is an interesting question that one can ask oneself, is really helpful, because I think following, you know, I think what you love or what you see yourself sort of like what is given to you or what you're called to, you see that the ways in which you know, the consequences of it can really surprise you, you know, and it's really something to be attentive to follow, and to try and keep following. Yeah, so I don't know if that answers the question. Maybe I was a bit roundabout, but yeah, I mean, I think that this is really something that you know, I mean, I think we all want our work to be meaningful, you know, and so it's something that, for me at least, is a very dear question to me.
Yeah, that's wonderful. Thank you for that. I also had a question of my own. So we start off this analogy with these topological edge modes, and so I guess my question is, it's I guess it's kind of clear why the edge is special, because it's sort of like a physical edge of a sample. But in your models, what kind of determines sort of what configurations lie on the edge? How's that chosen?
Yeah, that's a great question. And so let's see. So yeah, I mean, what is nice is that because these are like such physical changes of the system. So let's say if the system is it depends on what the change is. If the system is like adding monomers, so then it could be just like maybe there's like a solution and the polymer is growing by having monomers from the solution being added, and then when you finish the monomers in the system, or let's say it becomes too energetically costly to add another monomer, then that's an edge, right? So like it keeps on growing until it hits that edge. Or in this example where the edge was, let's say, converting a particular monomer. So in that case, once all of the monomers are converted, then you naturally hit that edge. So then that edge is probably, there's probably some kind of condition in which Y is bounded by X actually. So it can't go any further. So in that sense, these are like very real physical constraints that lead to the edge. Yeah, to this edge. So yeah, so that's kind of cool. And what is neat also is that because in chemical systems you may not get an abrupt edge, right? Maybe things just start slowing down. So that's also kind of neat. Maybe you have like maybe more of like some kind of like softer edge. So there's a very interesting questions here to consider what an edge means and how to model that.
Cool, thank you.
Julie, go ahead.
Yeah.
Hi, I have a quick question. I was wondering, in your perspective, what would you say is kind of the difference between information flow in physical and biological systems?
You mean like information flow in physical systems and information flow in biological systems? Yeah, that's a great question, and it's also a very big question, so I'll try to answer it. But then I'm also happy to discuss with you if you feel like there's a specific system you're thinking of or question you're thinking of. The first thing that comes to mind to me is that in biological systems, information is usually something that we are very oriented, that really changes the way in which the system moves, right? I mean, this is very evident to me because like I've studied learning, and learning is really sort of saying that there's tons of information, but we're also learning to like prioritize the information, right? So even something as simple as learning, I meet 5 people and then I maybe only get to know one of them better, right? Because that I realize that information is particularly important to me. I also realize, I use information to decide what I should focus on, and we do this all the time, like where to go, what to eat, what to do. And so biological systems really use information very strongly to move, to react, to respond, to for survival. So and somehow like in physical systems, like this is not as present, right? I mean, for a physical system, if you hit it in all different ways, it will it'll probably respond, let's say, depending on physical forces, but the information like who's hitting it or like it doesn't really matter as much. So I would say that biological systems are really motivated by information in a way that really leads now that information for biological systems, I think, has to now become part of the thermodynamic description in a way that you don't have to for physical systems, because now information can now be converted to things like work, or converted to things like can distinguish between things in a way that thermodynamically maybe we didn't need to do before, because we didn't need to consider the role of information before. So that's also one reason why I think information is important for biological systems. Yeah, it's just used a lot.
Can you elaborate on this connection between like thermodynamics and information? Maybe some people are not as familiar with this.
Yeah. So this is something that there's a few different ways to think about it, but specifically, I think well, just thinking about how Shannon was someone who started to put information on a thermodynamic basis, which is to think about where we're looking at an ensemble of a system, information can simply be evaluated as like P log P, right? And so thermodynamically one can define such a quantity, but then how does it relate with actual, what we think of as like actual thermodynamic quantities like energy and work and heat and all of those things that seem like more physically measurable. And so firstly, like mathematically it can be defined, but what we can also start to see, and I think this is most evident when you start looking at really systems that have stochasticity, because I suppose if you have systems that are like deterministic, then you're like, well, we don't need a probability distribution, and then you don't need to be thinking about information, things like this. But so this really started to come about when people started to be able to think about stochastic systems, especially when our experiments started getting better and better, and we could look at small molecules or small things that really fluctuate a lot, because now the thermal energy scale is sort of like that same level of fluctuations. And then when we started thinking about fluctuations there, what you can see is that information can directly relate to work. So I'll just give a couple of examples. Like some examples are that if you think about an expanding gas, and this was this concept of the Maxwell demon that is very interesting Gedanken experiments. So if you have a box with a gas molecule, and if you know where the gas molecule is, and then you insert a partition, and now the gas molecule has to expand and push that partition out. So the gas molecule is doing work that you could have extracted because you knew where to put the partition. So information could be converted to work. And then this can be repeated again and again, right? Then you see where the particle is next, you trap it again, and then it pushes it out. And this has been measured in systems like DNA folding. So firstly, that's one way in which information can be connected to thermodynamic quantities like work. There's also other examples where we think about the storage of information, that reading and writing information often requires a physical process, whether it's a molecule changing or some signaling thing changing. So there's a physical act associated with reading and writing information, and also erasing information, right? That's the other thing that we think erasing is like for free, but erasing information also requires some physical process, and so try to quantify that. And I think that's something that's very exciting, because we are in an increasingly information focused world, and I think as physicists we have a lot to offer there, because we can start thinking about like costs of energy writing and removal in a way that I think is really important, because otherwise now we treat information and information processing as something that is like disembodied, like I'm talking to you guys now over the internet, and it's like seems like it's all happening just like automatically, but really there's a cost behind. There's a physical cost behind all of these things, and so that's one direction in which that's been very interesting. This connection between information and thermodynamics.
Julie, go ahead.
Kind of as a follow-up question to that, this might be a naive question, but
no, go for it.
I'm wondering, like, how would you say information is created then? Like, I'm thinking about the transition between non-living and living systems or something like that. Like, where could it come from?
Yeah. Seems like a very profound question. Well, I mean, in terms of like creating information, I guess, one very naive way is that just thinking about like storing information, often you have to like denote something, right? So if I think about something as simple as the configuration of a molecule, that maybe says something if it's in one configuration, and it says something else if it's in a different configuration. So that is one way of storing information. And then, I think that your question is also about like, well, how does meaning or interpretation or response then come about because of this information? And that's a huge question that I think is also one of the big open questions that we have right now. I mean, a lot of people will use the word evolution as like, oh, it's evolution, sort of as if like that answers the question, and it's just like, well, we didn't learn anything more after you just said that word, but that is, but a lot of people, it is often said that the association of, let's say, a molecular configuration with what it does, this comes about through a lot of time and iteration, and like biological organisms start to recognize that, okay, if those molecules are in those configurations, maybe that means that fruit is better to eat than that fruit is rotten, because those molecules then are in that configuration. And so then people start to learn these things. So then it's all connected to learning, and then also evolution, because then systems become sort of optimized for processing or receiving different kinds of information. But this is like a huge topic that is definitely not, well understood. But yeah, that's a really great question.
So maybe on a slightly different note, you did started your graduate work on quantum Hall systems and and you transitioned to biology at some point, but like the theme of topology kind of carried over. Is this like an accurate characterization, do you think, or?
Yeah, that's a fair. I mean,
So
again,
what
my
do
path
you
tends to
think
be
prompted-
winding, so it wasn't just straight. But yes, that's more or less the coarse grain version of yes, what happened.
Sure. So what kind of led to your decision to move to this different field and kind of explore topology in this biological context?
Yeah. So yeah, I think why I moved in a different field was because I think biology has a lot of big open questions. Like even a question that Julie just asked me, how did the creation of information then start to get linked to the way that we process information? I mean, this is huge, and we don't understand it, and there's so much more tools that we need to build to try and understand this better. So I think I felt that there were a lot of big questions open in biology, whereas condensed matter is really beautiful. I clearly love it, but it is a bit more well studied, right? That like things are that there is more theory, so some things are better understood, and I think while I love quantum systems, like that question that I was talking about, what does this have to do with the real world? I think was still a big one for me. And I'm not saying that quantum systems don't have anything. I mean, they do. They're hugely important for the real world. But I think for me, I'm an impatient person. I think I wanted to see it in a more sort of direct way. And so that's part of the reason why I switched to biology, to look for questions there. And then that was the Wild West. Oh my gosh, where do I start? And so I will say that yes, but I still have always loved topology, and I think that's still very much a part of me, in the sense that I'm trained as a physicist. I really love these very sophisticated and very beautiful theories. Even if biology can seem pretty messy, I'm still no, wait, is there a structure underneath all of that mess? And that's something that's sort of impelled me to try and find structure underneath all of that seeming mess. And as to topology and biology, I will say that it's very exciting for me right now. But this is also I didn't plan it, and I think that's one of the amazing things about research. Of course, I was this is something that would be a lot of fun. Of course, that now that we found it, it's this is amazing. But when you do research, you can't always plan that I'm gonna find something. I mean, yes, of course, I tried and I worked on it and I tried in different ways, but I was also trying. I mean, I'm also working on different things, right? Like information and learning, and right now I'm super excited about topology because this is some new results that I'm really excited about. But I guess what I'm saying is that I clearly love topology, and I think it's very powerful, because of all the reasons that I told you, these robust edge states, the fact that it's I think it's the emergence of these states is also something that's really very, very, very strong, and also that we do have a lot of good theory from quantum about topology. So I think there's a lot of reasons why it's a very attractive theory. And so yes, I mean, of course, I'm really excited that I can study two things that I'm really interested in, right? Topology and biology. But I'm just going to say that it's that I'm excited that this is where the work is right now, but it's not something that I could have planned in that sense. Sorry, I don't know if this was your question, but I just wanted to say that it's not like I was oh, I'm going to be talking to people about this in 2 years. I mean, it's hard.
So maybe as a slightly different way to ask it. Okay, this is a different question. I think you have this common theme, kind of technically. And it seems like some of the similar concepts come about in terms of edge states and whatnot. But What do you think are the like kind of salient differences in your work that you see between studying something like a quantum Hall system or like electronic systems versus or condensed matter systems just broadly, or in biophysics? Like, do you see a difference that manifests like experimentally, or like, yeah, how does that kind of play?
Yeah, that's a very interesting question. Yes, I would say all of the above, in the sense that, well, solid state systems or condensed matter systems, yeah, again, we have more theory there. So I think we understand, well, we are still finding new things, but the lattices that we have, because there is more theory there, so I think a lot of the more basic questions, sort of like if you just like randomly stumble upon some metal, probably will already mostly understand what it does, whereas if you randomly stumble upon some biological system, that's not true. So just a lot of things have been worked out for condensed matter systems, and so that's just a matter of like where the field is. But in terms of the implications, also just for like day-to-day interacting with these systems, I would say that, yeah, biology is often can be really flexible, so even when Chris asked me like, well, what is an edge, like I was like, well, it could be this, it could be that, and that's just interesting that there's several ways in which there could be an edge, in these systems, and there could be dynamical edges or soft edges, and so that's just really interesting because it starts making you think that like, all right, like the theory that I thought was understood, oh my goodness, there's like different ways in which now actually like we need to like explore different things about the theory. So I think the flexibility of biology, because biology exists in so many different forms and so many different systems and organisms, really can open up a lot of questions to investigate. In terms of experiments, yeah, I think that is something that could be also really nice, that in biology, a lot of times, like firstly, like the energy scales don't have to be as low as in a lot of like, well, cold atoms or in electronic systems. And that's really nice also, so like, one could maybe, do some experiments with more easily without having to like, like set up a whole dilution refrigerator or set up this or set up that. I mean, of course now, with graphene, there are lots of ways in which one can do also simpler experiments, but still a lot of times, like, so I would say just like the energy scales, biology can make things more accessible. And a lot of these, yeah, these are molecular systems. So again, just the wide variety that we have of them could provide more, sandboxes for playing in potentially.
Okay, yeah. So maybe I'll finish up my question with a follow-up, that really wonderful response with the question that like I've often heard something like biology has, okay, like a long time ago people would say condensed matter physics like squalid state physics, and that obviously has turned out to be extremely false over time. But it seems like the same physicists will turn around and say something similar about like the lack of structure in biology. So you'd say this is due to kind of the underdevelopment of theory in this direction, or because of like experiments aren't clean enough, or like we're trying to probe experiments that are getting more insight or something like that? Yeah, do you have any thoughts on this question?
Yeah, I mean, I think that's a great observation, and I would say that that's probably true, but I do think that biology is messier than solid state, right? Just as like solid state is messier than the standard model or whatever it is, but at the same time, like it's also like like human curiosity, right? Like we're always wanting to go further, like we went to the moon and then it's like, all right, now what's next? Like even though it is probably messier, but at the same time, we're not going to be content to just saying like, all right, like now condensed matter is like cleaner. Okay, I'm going to sit at home and lie on the beach. I mean, no, like we're just going to be like, no, well, that's now like the amazing thing that I think that looking at condensed matter gave me is like, oh my gosh, the fact that we can actually describe like these systems that actually, yeah, solid state can appear pretty messy sometimes. Like we can describe them actually so well. It's like, well, does it like give us confidence now that we can now jump into something that's like really crazy and see what we can do there, and so And so, yeah, it's definitely a lot to be done, but and you know, I'm not saying we're gonna like, you know, like in 10 years biology is gonna be like cleaner. I mean, like it's gonna take a while, but it's also there's like, well, let's see what we can do, you know, and let's see like how much we understand, because then this also makes us have to rethink, right? Well, do we really understand emergence? Do we really understand, you know, like interacting systems? These questions.
And but you think this sort of like yeah. So you think the development is mainly theoretical or like kind of deeper probes, like in the fields that you study? Do you think? Yeah.
For sure it's both. I mean, that's, well, I would say the fun part about physics is both, but I would say that the reason why I love topology is because it's I mean, to me at least, what I see is one of the few places where theory can lead experiments, you know, because so often, right, like in physics, it's like, all right, you know, here's this phenomena, okay, theorists go and figure it out, you know, but it's already been measured, you know, whereas topology is really one of these places in which, yeah, you know, so much of the theory led the experiments, you know, and that's really exciting. And in biology, it really, really rarely happens that theory can lead experiment. Usually, like the biologists are like, okay, you know, you poor physicists, you know, we have all these like fancy, you know, missions that we are doing, and you know, you guys can come and like help us like understand the things that we already measured, and which is really great. You know, that's hard work and that's necessary work, and that's great that someone can do it. But the idea that theory can actually sort of like stand alone and push experiments is really unheard of in biology, and it would be amazing, you know, if we can do this and try and show that it's possible.
Well, thanks so much for your answers. So we are running short on time, and also it is very late in Germany. So we'll start wrapping up. Do you have any final words of wisdom for us?
Well, no, I mean, it's been really amazing to hear your questions. I really, you know, I'm so impressed, because, you know, I think like that's one of the best things about being able to go forward, you know, just asking questions, asking good questions, keep on asking questions, you know. And I say this because a lot of times as students, often like one is like self-censoring, right? Like, oh my gosh, like, am I seeming like an idiot or something? So it's amazing that you guys are asking great questions. I'm very impressed. You know, I'm trying to come back to the US actually. So if any of you looking for positions in the future, you know, please get in touch. Yeah, it's been really, really great meeting and interacting with many of you. And also good luck, because I feel like a lot of you have very exciting decisions and careers and research ahead. And so, yeah, I look forward to seeing you at like APS or other conferences, or just hearing how things are going and what you're discovering. It would be really fun. So yeah, this has been a lot of fun for me.
Thanks so much. That was really, really nice of you. Okay, so yeah, we'll see everybody next week. We'll send out a reminder. I think we have people talking about very high energy physics now. So probably people talking about black holes next week. So stay tuned for that. And with that, take care, everybody. Have a nice week.